Let's tackle the TRX Row. So this one is actually a complicated motherfucker to have a look at. So let's start by drawing the guy out, figuring out what forces we've got available to us, and then start working through the problem of how we solve for them. So let's say we've got this wall here, the floor over here. Let's say I've got a head, a body that's coming like that, and then my TRX is, let's say, attached there to an arm there. So the question is, in this TRX row, what are we dealing with? Well, let's start working our way through. So again, let's say we've got a center of mass somewhere here, and we know that's going to be heading downwards because we've got the force of gravity acting on this mass. So let's call this the force center of mass. And the force center of mass is going to be equal to mg, mass times gravity. Let's say this person is me. Let's say they're 90 kilos. So we've got 90k, 9.8 meters per second squared. So this force is that times together. Fair enough, that's what we've got. Okay, so what else is going on in this particular thing? Well, we've got a TRX strap, a suspension trainer. And so we know that this is trying to pull upwards. So I've got a force coming back up, and we're going to call that T. T is for tension. And we don't know what T is yet, but we know it's going in and along the line of the strap. What else have we got? We've got a contact point with the floor. So we know the floor is pushing up with some amount, and we're going to call that N for the normal force, because that is generally in physics what we call the force that is coming up from the surface of the floor of something. We could have a normal force pushing off this wall. In fact, we'd have a normal force here, and we've got this normal force at the foot. We've also got, because this center of mass is behind the base of support, which is the foot here, there is a certain amount of this force that is trying to go in this direction. So there is a force acting on the foot of friction going in this direction. I don't know how much it is at this point, so let's call that F sub F or F sub friction. Okay, have we got anything else going on? Yes, we have something else going on here. So this guy has components now, because we can start thinking about this in terms of torques as we looked at with the other guys. Remember, no movement, which means the sum of the forces must be zero. So the sum of X and the sum of Y and the sum of the torque must be zero. So we could put that over here. The sum of force in the Y is the vertical component, must be zero. Otherwise we'd be traveling up or down, and we're not. The sum of forces in the horizontal, the X, friction here and this one there, they must also add to zero in this static position, because again, we're not moving. And the sum of the torque must also be zero, because we're not rotating, and this thing would like us to rotate. So I'm going to start with the torque side of this particular one, and we're going to take the foot here as our axis of rotation. So then what we're going to want to look at is, this is going to be our lever arm, right? This distance straight through the body to the center of mass. And there's a certain amount of this force of the center of mass that is trying to move us. That's not quite at 90 degrees, but we'll go with it. That is creating rotation around that. And then there is another component of this force that is going straight down the lever arm. So these are our components of force. Now, this component of force down here, pushing down into the ground, is what's giving us the normal force, or at least the vertical component of this is giving us the normal force, and it's also giving us what's going to be creating the friction response. But we'll ignore that for now. So we're going to call this the F center of mass X component. X component, the amount going down here. And then we've got over here the F center of mass, and I've really drawn that in a really crap place, so let's just rub him back out and go F center of mass sub Y. That is the Y component relative to these things. Now, we don't have to call that X and Y. We could have flipped those around. You could call them whatever the hell you like. But that's what we've labeled them for now. And how are we going to know what they're doing? So we then need to know what this angle is here between this lever arm and the center of mass heading downwards. And we know it's heading down because it's gravity, always going straight down to the center of the earth. So this angle is going to help us to determine how much of this force is rotational and how much is pressing just down into the ground. If the center of mass was right above the foot, there would be no rotary component. All of that mass goes straight down through the axis. So it is this component, because this line here is the same as this line here, right? Because we could make a rectangle. If we know anything about rectangles and geometry, that is the same as that, which means this length of this side of the rectangle or the triangle is the same as this one. And we can use some trigonometry, because we can go, if we know this angle, then we can also, and we know what the hypotenuse is. And the hypotenuse, as you can see, the long part of the triangle, is the force of FCM, the center of mass force. That is what that guy is. So FCM sub y is the part of the triangle that is the base of it, which is the sine of this angle, because the sine is the opposite divided by the hypotenuse. So if we want to know what FCM sub y, it is equal to mg, because that is FCM, times the sine of whatever that angle is right there. I'm going to say it's 25 degrees, just eyeballing it, okay? So we can then calculate how much is fighting on that. Cool, we know that. Well, that's not a torque yet, that's a force. Torque requires not just the force, but also a perpendicular distance. So we can plug this in here, that's our force. Now we need to know what this is. So what's this distance between the ankle and the center of mass itself? I roughly measured this in myself using 15 centimeter rulers, and it came out to about 1.05 meters, right? So I can then plug this in, I can get rid of that because that's that. So now I have this number times 1.05 meters, and that is now my torque that this force is creating around this axis. And it is that this is going to be fighting, because that is pulling in this direction. You can see that they're opposing on parallel lines. The tension in this is going to be the thing that is fighting this. So let's just scribble in mg sine 25 degrees times 1.05. That is the torque of the center of mass. Let's call it that. So now we want to know the torque of T, the torque of the tension. So that guy is going to be equal to the force of T times its distance. Now again, roughly done on me with tiny ass rulers, just stacking them and getting somewhere nearby, was 1.35 meters. Okay, and we know, because again, the sum of the torques must be 0, that the torque from the center of mass must be equal to the inverse of the torque from tension. We've done that in videos before. So we could plug in our definition of what this guy is. So we've got mg sine 25 degrees times 1.05 meters is equal to whatever T is, and we still don't know what T is, times 1.35 meters. And again, as we've done in other videos here, we're going to get rid of this. So we're just trying to get T by itself. So I'm going to divide by 1.35 meters. That's going to cancel on those guys, but I did it to there, so I have to come and do it over here. So I've got this, and this equation is going to give me T. It's going to tell me how much load is in the hand on the TRX Row. So let's get the calculator out and do that. All right, plugging in mg, so we've got 90. Okay, so 90 times 9.8, that's the force of gravity, times the sine of this angle right here, sine of 25, times then the perpendicular distance, the lever arm, straight through the body, 1.05, divided by the perpendicular distance to this time the shoulder, where that guy is. I'm going to take him all the way up to there, and that is 1.35 meters. And that's going to give me the force in this guy right now is going to be, so let's put this down here, T is equal to 290, slightly rounded up, newtons. To put that into kilos, let's divide by the force of gravity, so divide by 9.8, and we have basically got, let's round this slightly up, 29.6 kilos. So the load we are dealing with in this strap is dependent on how far this starts to get across, because then more of the force currently is being supported by the feet than the strap. And that makes sense, right? Like as you lean further and further this way, it gets heavier. You kind of know that from experience. And the reason it gets heavier is this distance that the center of mass is away from this support foot increases, and therefore it has to then be supported by this guy. You could look at this a bit like a push-up, or like the rack chin that we looked at. It's no different in that regard. Where this one gets more complex is starting to play with, okay, so the force of N, and we're going to need more angles in this. So I'm actually just going to outline this rather than do this precisely. But T itself has components, right? It's got these components. So it's got a certain amount, if that was a straight line, of this force is pushing across horizontally, and a certain amount of it is pushing up, or pulling up, I should say, vertically. So T has T sub X and T sub Y itself. And then this F, here's the weird one, or the complex one. The F, center of mass X. Center of mass X, which is itself mg, because it's the force from the center of mass. Now, we said that FCMY was the sine, FCMX is the cosine, because the cosine is the adjacent over the hypotenuse, so it's the cosine of 25 degrees. Okay, cool. So that, whenever we see FCMX, is that. Well, N is responding to FCMX. So then we have this other thing, but FCMX is not completely vertical. It's coming at an angle, which means when it hits here, it itself has a component, when it hits the floor, that is vertical and a component that is horizontal. FCM does that. And so the responses of these guys are in response to that. So we then have to start going, okay, well with this guy, now what's the angle between here? And we don't necessarily know what that is. We'd have to measure that and go, okay, so if that's the angle, then this time the upwards force is actually the cosine. And you can't really see that from here, but it's adjacent to it. So if I wanted N is equal to FCMX times cosine of, I'm going to call it alpha, whatever that unknown angle is right there. But this is, again, getting squirrely, because what that is really equal to is this times this, right? So we've got mg cosine 25 degrees times cosine of alpha, that is N. And if we wanted to know friction, we'd have to go, let's call this F sub F, is equal to mg cosine 25 degrees, because again, that's the force coming down, and that's trying to push that way, that friction is fighting. But instead, friction is now the sine of that. It's the opposite bit. It's the bit that's coming across from this guy. So now this one is times the sine of whatever this unknown angle is right there. So that starts getting squirrely, as you can start seeing. And we could then do the same of these guys. And the amount of weight being lifted up, well, Ty is lifting upwards. So some of this mass is also not pushing into the floor, because it's being supported and lifted by that guy, which again kind of makes sense, right? Like if we're holding on to something. In fact, you could, what would happen if you lifted your feet? If you lifted your feet, you'd pendulum, you'd start swinging that way, because there's a force pulling, a centripetal acceleration that goes in this direction, while gravity is accelerating down. So you do a pendulum, and you will slam into the wall over here. But it's clearly supporting at least that upward pull. You don't drop straight down. So some of the Y components of force are supported by the Y component of tension of the TRX. Complicated one, right? But as far as we're concerned, for answering the basic question of how much weight am I lifting, all I need to know for that, assuming there is enough friction in the floor to stop you sliding along, and that might mean that you need to put trainers on a wooden floor or on some carpet, or you might need to put your feet right against something that won't move, you stick them right against the wall, whatever it is, if we've got enough friction there, we can then ignore that as far as we're concerned for exercise in the gym. And we're just interested in this torque component, which is this guy round here. And so how much we're lifting on the TRX is quite simply a result of how much the center of mass moves away from the base of support being the foot. It is then taken up by that guy, and that is what you are lifting. Easy way for you to make this harder if you're at home and you're doing loads of TRX rows and you can do 20, 30 reps, is to just add weight to you. Get a backpack, sling 10 kilos in it. That is now a part of your center of mass and is the equivalent of you progressing that move. You could use a weighted vest. That's a more symmetrical way of distributing that load. But the cheaper one is backpack and sling some weights in it. It's definitely something I've used for clients and it works really effectively. But hopefully that makes some sense on the TRX Row.